Have a nice day, everybody. I'm Daniel Barrett, and the title of the paper is A Large-Scale Homography Benchmark. The main motivation of this paper is that there are no large-scale benchmarks for homography estimation. So actually, there are only a few benchmarks. For example, the Homog dataset, which contains 16 image pairs in total of well-textured areas, or the H-patches dataset, which has more image pairs actually, but half of the dataset exhibit only illumination changes, and the other half exhibit only baseline changes. And again, these are all showing well-textured areas where homography estimation is a particularly easy task. Also, there is the extreme view data set, which is very challenging actually for both for homography estimation and feature matching, but it contains only 15 image pairs in total, which is again not enough for benchmarking homography estimators, training homography estimators. So the main motivation of the paper is to provide such a data set which allows for all these things which I mentioned. So basically what we did, we took the 1DSFM benchmark, 1DSFM data set, we ran CallMap on it to get us past with the reconstruction. Then we did manual checks to make sure that the reconstruction didn't fail, and therefore we kept only 10 scenes. And we also did scale annotation to get a metric reconstruction. And this we did by checking the scales actually in Google Maps, then averaging the scales, and this is what we had, and this is how we got the metric reconstruction in the end. From this metric reconstruction, we ran Progressive X Plus, which is a multi-model fitting algorithm, to get 3D planes and point to plane assignments in this reconstruction, as you can see here in this example. So here color assigns points to 3D planes. And from this, basically, we iterated through the potential image pairs. In each image pair, we checked if any of the planes are visible in image. If yes, then we selected feature correspondences that are consistent with the homography that the plane implies. So we basically selected ground truth correspondences for the homography. And then we made sure we only kept those image pairs where the actual ground truth homography can be estimated from its ground truth layers accurately and in a way that it leads to good camera poses when the homography is decomposed to relative pose. By doing this procedure, we created the homography estimation benchmark dataset, which consists of 200,000 image pairs, which is significant orders of magnitude more than what previous databases have. Also, the image pairs exhibit various realistic camera motions coming actually from this SFM dataset. Also, they exhibit various illumination changes. Also, it is very challenging for robust estimation. Often, image pairs have lower than 1 or 2% in error ratio. And they also define a train and test split, so homography estimators or other algorithms can be trained or fine-tuned on this dataset. We did lots of benchmarking and different kind of applications. The first benchmarking which we did is basically benchmarking traditional robust estimators. Here you can see the horizontal axis is the average time, the vertical axis is basically the accuracy. And you can see, like, for example, when there is the left plot is without SNM pre-filtering, the right plot is with SNM filtering. Without filtering, the affine GC rensec shines, it has the best accuracy. With pre-filtering, VSEC with PROSEC is the best. Also, we did benchmarking for different kinds of deep pre-filtering methods. This is what you can see here. And you can see that basically ORNet with VSEC PROSEC leads to the best accuracy on this dataset on hundreds of thousands of image pairs. Also, given all these methods, we were able to perform some benchmarking in different metrics, where we got that the inlier numbers are not and not very correlated with the relative pose. Also but the angular relative pose, where we calculate the translation angle instead of the metric distance, it is actually quite well correlated with the actual relative pose error in meters and rotations in degrees. And we have such conclusions in the paper. Also, this slide had earlier, we did another application for because this data set, because we had the graph through homography, we are able to decompose the homography to local affine correspondences in each correspondence. So we can get the uncertainty in different components obtained by feature detectors. For example, SIFT obtains, besides the point positions, it obtains rotation and scale for the features. And previously, there was no way of verifying how accurate this scale and orientation is. And by using this dataset, we can actually analyze different properties of the feature detectors and of the affine components of the feature detectors. You can see here different kind of histograms of the reprojection errors, of angular, of the orientations, of the scales. We obtained that this positional standard deviation of SIFT features is this pixel value. We have this orientation error and this scaling error here. So basically, this data set is perfect for understanding feature detectors and analyze their behavior and noise. We have, of course, statistical data set. You can see at the top the training set, bottom the test set. You can see that various inlier ratios are present in the data set, but the majority is in the low inlier ratio part. Also, in the right part, you can see that the angle between the camera and the surface normal, representing the homography, like the entire range is well covered, both in the training and test set. Also, you can see that we have not just different inlier ratios, but different inlier numbers as well. And in most of the cases, the inlier we only have a few tens of inliers, which makes it very complicated for robust estimators. Thanks for the attention. I hope it was understandable.